Good evening. Our topic today is under the chapter Semiconductor. I've already put up a video, the first one, where we discussed about semiconductors, the N-type and the P-type semiconductor. And this is the second part of that chapter, where today we're going to discuss about the formation of a PN junction. But before we start that, let me just, I hope you remember what you mean by a P-type semiconductor and an N-type semiconductor. In a P-type semiconductor, we dope the semiconductor with a trivalent impurity, because of which we have a number of holes greater than number of electrons, and therefore holes are the majority carrier and electrons are the minority carrier. Whereas in an N-type semiconductor, we dope the semiconductor with a pentavalent impurity, and therefore number of electrons greater than the number of holes, and electrons are the majority carrier, and holes are the minority carrier. Now, both these holes and electrons become charge carriers in a semiconductor, and the total current in the semiconductor will be due to the total current will be the current due to the holes plus current due to the electron. Let me just try to explain to you how both electrons and holes can be charge carriers in a semiconductor. Now here I have drawn a rough diagram where a semiconductor, this is a pure intrinsic semiconductor. There are no dopants here. What I have drawn is a completely pure silicon semiconductor, intrinsic semiconductor. And I have only drawn the valence shell of the silicon with 4 valence electrons. Okay. Now at T equal to 0 Kelvin, all the electrons are bonded electrons, and there will be no electrons in the conduction band. All the electrons will be in the valence band, all of them. This is now there, okay. So the conduction band is empty, but the valence band is full. Now suppose you give a temperature greater than 0 Kelvin, then you know that some of these electrons can get enough energy to break free from their bonds. Like for example, let's say this electron becomes a free electron, creating a hole or the vacancy of an electron in the valence band. Such a free electron will now appear in the conduction band, and corresponding to that electron, let's say this is the hole that has appeared in the valence band. Okay, so the hole so you have an electron hole pair where this electron has come because of T greater than 0 Kelvin, and you will have those holes. Now if there are 1, 2, 3, 4, 5, 6, 7 electrons, there will be 7 holes in the valence band also. I haven't drawn that. So there will be 7 holes, 3, 4, 5, 6, 7 holes corresponding to the 7 electrons which are free electrons in the conduction band. There will also be bonded electrons in the valence band. Okay. Now if you connect this to an external terminal, an electric field with a positive here and a negative here to the battery, to the supply, you will see that you are now applying so this is the positive end, this is a negative end, and you are applying an electric field in this direction. So electrons will always move in a direction opposite to the electric field. So what happens to all these free electrons? I've only drawn one. Let's say there are 7 of them have got enough energy to become free electrons. Okay. So now what happens is, I've just drawn 2. Then let's say lots of free electrons are there. All those free electrons must now, under the electric field, move towards the positive terminal of this battery, and so I've shown you that these free electrons are now moving in this direction towards the positive terminal. You know that the conventional direction of current will be opposite to the direction of flow of electrons. So the current due to the flow of electrons I've shown like this, opposite to the movement of electrons, and that's why I've shown IE in this direction. Okay, so these are the free electrons that are moving towards the positive terminal. Now all these holes are present here. I have not drawn all the holes, I have just drawn 2 of them. Now because of this hole here, a neighboring electron in the which is bonded, this bonded electron, seeing this vacancy, can move here, filling up this hole, creating a hole here. Similarly, from this neighboring here, this electron can move here, filling up the hole here, creating the hole here. Then now let's say the neighboring electron from here has filled up this vacancy, but the hole has moved here. Like that, you will see that as the electrons move to the left, the holes keep moving to the right. Let's say this hole has reached here. This hole has moved up to here. Actually, it is not the hole moving because of your neighboring electrons, the bonded electrons jumping in to fill up the vacancy. That is the hole. You feel as the electron moves to the left, the hole is moving to the right. So an electron from this, there is excess of electrons here, right? So these electrons will now move in this direction to fill up this hole. So you will see that now you have movement of electrons from the negative terminal to fill up the hole that is actually moving into the right. So this electrons moving in this direction, you know current will be in the opposite direction. So you see that this I have marked as the hole current which is in this direction now. So hole current, the holes are not actually moving. Only thing is when electrons here, this now there's a hole here. Let's say there's a hole here. This electron will jump in to fill it up. You will see that this is hole here. Now this electron can jump in to fill this. So when this becomes filled in, the hole will travel here. Now this electron will, let's say, jump in here, filling this up, creating a hole here. This electron will jump in to say creating a hole here, and this free electron will now get enough energy to jump into the conduction band and become free. So you will see that in the external circuit you have the current due to the electron and current due to the hole in the same direction. So the total current is going to be the current due to electron plus the current due to the hole. So you will see that due to the movement of electrons in the valence band, you feel that when the electrons are moving to the left, the holes are moving to the right, and therefore there is a current which is called the hole current. Also you have these free electrons moving towards the positive terminal, which is what you call as the electron current, and the total current in this semiconductor will be the electron plus the hole current. The same thing applies for extrinsic semiconductor also. So I hope you've understood that in a semiconductor, you can have electrons and holes as charge carriers, and in an n-type semiconductor, the number of the electrons are the majority carriers and the minority carriers are holes. But in a p-type semiconductor, the holes are the majority carrier and electrons are the minority carrier. Now today we are going to look at the formation of a p-n junction. Now, if you take a wafer thin semiconductor like silicon and dope one side with a p-type with a pentavalent impurity and the other side with a trivalent impurity, you will get what you call as a p-n junction. So, let's say we have a silicon wafer thin silicon semiconductor material. You have doped this side with a trivalent impurity, so that this is the p-type. And here you have doped it with a pentavalent impurity, so this is the n-type. And the junction between these two is what you call as a p-n junction. Now you must know that here we have the majority carriers as electrons, and here we have the here we have the majority carrier as holes, and here we have the majority carriers as electrons. N-type has majority carrier electrons, p-type has majority carrier holes. Now you also remember that this n-type would mean that we have doped it with a pentavalent impurity. So we have a arsenic surrounded by other silicon atoms. We have silicon here, we have silicon here, here also, and here also. Okay. So we have all of these electrons in bonded to the covalent bond, but arsenic has an extra electron which cannot get into bonding, because arsenic, as you know, is pentavalent and we need only 4 of those electrons to complete the octet. So one electron is already a free electron. Now, even though we call it an n-type semiconductor, because number of electrons greater than number of holes, the problem here is we know that we didn't add an ion. This arsenic has 5 valence electrons. Corresponding to those 5 valence electrons, arsenic has 5 protons in its nucleus, right? So, now if you apply some temperature, you will see that you will get a hole here and a free electron. So number of free electrons is greater than the number of holes, agreed. And so we call it as an n-type semiconductor, but it is not negatively charged simply because corresponding to this extra electron, we have 5 protons in the nucleus of that arsenic. So what we added is a neutral atom. Only thing is, because this could not get into bonding, it became a free electron. Similarly, on the p side, we have doped it with, let's say, boron. And boron is sharing its electrons with the neighboring silicon. Okay, we have silicon here, we have silicon here, we have silicon here, and also here. I've just drawn one boron. Now, here we have complete octet here like this. Now, problem is boron has only 3 valence electrons. So, 3 of them have contributed to the covalent bonding. But here there is a vacancy. Let's draw it here. Here there is a vacancy of an electron, which is what you call as a hole. So, when you supply temperature, let's say one broke free and there's a hole here and there's an electron. So, you will see the number of holes greater than the number of electron, and therefore we say it is a p-type semiconductor, but it is not positively charged because even though we have a hole here, corresponding to this, there are only 3 protons in the boron nucleus. So, boron has 3 valence electrons. Corresponding to that, boron has 3 protons in the nucleus, corresponding to the 3 valence electrons. So, what I'm trying to tell you is, this is actually neutral. This electron is here, actually here. So, there is no extra charge here, no extra positive charge here. There is a hole here, which is the absence of an electron. But corresponding to the 3 valence electrons of boron, boron has 3 protons in the nucleus, making it a neutral atom. So, even though we call it a p-type semiconductor because the number of holes greater than number of electrons, it is actually a neutral atom. Okay. Now, when you bring the two p-type and n-type together and there is a junction between this p and n-type, naturally, because there are majority holes here and majority electrons here, the electrons will diffuse from n side to p side. The electrons are going to move this side. And I told you, as electrons move to the left, you know that the holes are moving in the opposite direction, to the right. So, electron movement to the left would mean holes are moving to the right. So, you may say electrons are moving from the n to p side or holes are moving from p to n side. Now, when that electron from here moves to the p side, what is happening here is this free, okay, I'm sorry, let me fill this up and let the hole be here. So, that's easier for me to show you. Now, this free electron is actually this one, okay, free electrons combining with a hole, that's a hole on the p side. So, this electron now combines with the hole here. So, what has happened is, this arsenic has lost its electron and boron has gained an electron. Arsenic was initially a neutral atom with 5 protons in its valence shell corresponding to, in its nucleus corresponding to the 5 valence electrons. Now that it has lost its electron, free electron, it now only has 4 electrons but 5 protons in the nucleus, making it a positive ion. So, for every electron that crosses over, you are creating a positive ion, which is, this is actually called the donor atom because it can give an electron. So, this is called a ion now, positively charged immobile ion, which is the donor ion. Okay. Now, this boron that accepted this electron actually has only 3 positive charges, protons in the nucleus corresponding to the 3 valence electrons it had, and it was neutral. But when it accepts an electron, it now has what? 4 electrons in the valence shell, and corresponding to that, it has only 3 protons in the nucleus. So, now it has become a negative ion. So, for every hole, that is electron combining with a hole, you are now creating a negatively charged, this was called the acceptor atom because it can accept the electron. So, you have now created a negatively charged acceptor ion, which is an immobile charge. It can't move. It is an ion now. So as electrons cross over, you are now creating positive charges, immobile charges on the N side and negative charges on the P side. Okay. Now you can draw one more layer also. I'm not wasting my time here. So for every electron that crosses over, you are creating immobile charges at the junction, and these atoms have actually lost their majority carrier, right? These charges have lost their free electrons, which was a majority carrier. These atoms have lost their holes, which was their majority carrier, and they have now become immobile charges, which are ions. And you will see that this region is therefore called it is either called the space charge region, or it can also be called the depletion region. Why depletion region? Because these ions are atoms which have been depleted of their majority carriers. Okay. Now, because there is positive and negative, you see it sets up an electric field. There is an electric field which is set up across the junction. This electric field is actually, see, if you look at the electric field, you know that electric field, the movement of electrons are always opposite to the electric field. So our majority carrier so when the majority carrier electron was crossing over from the N side to the P side, that current is called the diffusion current. Diffusion current is a current due to the majority carriers, that is electrons moving from N to P and holes moving from P to N, and that because of the movement of electrons, you will now, so electrons are moving in this direction, so you will have a current in that from P to N. You will have a current flowing, and that current is what you call as a diffusion current. Now, when this electric field is set up, you will notice that this actually opposes the crossing over of electrons from N to P, right? Because electrons always move in a direction opposite to the electric field. So, your majority carriers electrons can't move to the P side from N side because your electric field is in this direction, which is opposing the movement of electron from N to P. So, as this more and more electrons cross over and this depletion region becomes wider, you will see that, and that means the electric field is becoming stronger. As it happens, you will see that the diffusion current starts to decrease, because this electric field opposes the further movement of electrons from the N side to the P side, or the movement of majority carriers. The diffusion current is a current due to the movement of majority carriers. Okay, so now you will see that on the P side we had minority carrier, that is electron, and here we had the minority carrier. N side has minority carrier holes. Now when this electric field becomes when the depletion region becomes wider and the electric field becomes stronger, this electric field is now favoring the crossing over of electrons to this side, from the P side to the N side. Because you know electric field, the electrons will move in a direction opposite to electric field, right? So such an electric field will now pull these electrons from the P side to the N side. That means we have the crossing over of the minority carriers. Minority carrier electron from P side to N side, and minority carrier hole. So as electrons move to the right, the holes will move to the left. So now we have the crossing over of the minority carriers because of this favorable electric field, and that current is what you call as the drift current, and the drift current under this electric field will increase, and at some point you will see that the two currents are in opposite direction, right? This diffusion current, so we have electron diffusion in this direction and electron drift in this direction. I'll write it here for you. Electron diffusion is in this direction, whereas electron drift, I'll write it here. Whereas electron drift is in this direction. What is drift? Minority carrier current, right? So here P side, the electrons are the minority carrier. So that's why I've shown electron drift in this direction. Here electrons are the majority carrier. So when they cross over to this direction, I've shown you electron diffusion in this direction. So current, as you know, is in the direction opposite to the movement of electrons. So you have a current, diffusion current in this direction and a drift current in this direction. The two currents are opposite in direction, and at some point the two currents become equal and the net current across the junction becomes zero, and then the junction or the PN junction is said to be in equilibrium. Okay. So this is the formation of a PN junction. Now also something else you must remember is there is a potential difference at the junction, right? See, we have, this is a positive end and there is a negative here. So that means there's a potential difference across the junction, and that potential difference across the junction is what you call as the potential barrier or called the barrier potential. And this potential barrier is the potential difference across the junction that behaves as a barrier. Or what do you mean by a barrier? Something that opposes. So this potential behaves as an opposition or barrier to the movement of majority carriers across the junction. You will see that as this potential becomes larger or the electric field grows in strength, it opposes the movement of electrons, that is majority carriers, from the N to P, that is electrons from N to P. That means it opposes the diffusion current. So that potential which opposes the crossing over of majority carrier is what you call as the potential barrier. Now if I draw the two sides, you will see this is at a higher potential, this is at a lower potential. So across the junction, you will see there is an increase in potential, and this difference in the potential between the P side and the N side is what you call as the potential barrier, which we denote with V0. It's also called barrier potential V0. So you see this is at a lower potential, the negative side, and this is at a higher potential, and this difference in the potential difference, this difference in potential between this P and N between the junction is what you call as the barrier potential or potential barrier. Thank you.